Hi, June.
Mhm. Hello. Oh, sorry.
Hi, June. What's up?
Hello, everybody. Can you hear me?
Yes, we can.
Okay. Hi, Gitas. Welcome.
Yes.
Thank you for coming. And I'm now making the co-host, and please, as usual, help me to maintain the session.
Okay.
Yes. We still get people join. In the meanwhile, if you have any questions, please take this a few minutes to ask me, and I'll try to clarify things. Any questions so far? Well, you can also, well, where is that? You can also type your questions in the chat box. I will try to um, attend that as well. Okay. Okay. Oh, get my windows organized, and now I'm start sharing my screen. Is my screen visible?
Yep.
Okay, it's good. So we still have people join. Well, anybody, if you want to ask me some questions, let's make use this a few minutes. or if you like to share some interesting story about your study or even your life.
June, I think you have a question in the chat.
Oh, sure.
It's
Yes.
about the assignment.
Yes. It's the short answer is yes. I will talk about assignment 2 today. And you can see that we have already get the assignment published on our Canvas site. Which Canvas site? Let me check. Assignments. And let me change it to student view. Now this is what, no. Okay, this is what it looks like from your view. Now we have assignment 2. I will talk about this assignment today. How can I exit the student view? I get a question, how do I feel after my job? No, not today, next week. Hopefully I will be coming to the session in with all my parts good. So yeah, bear me for a few seconds because now in Australia it's getting warmer. I don't want my computer to die in the middle of the session. I just turn on the air condition. Okay. Oh yes, now we have been 5 minutes into the session, so maybe it's a good idea to start. Good afternoon, everybody, and welcome to the 5th session of our exciting journey in machine learning. First of all, I have just received some of our students' feedback yesterday. It's awesome. Thank you very much for giving us suggestions and comments. I haven't enough time from then to now to respond specific ones one by one. I will try later in this week and give you a more detailed feedback, not feedback to the feedback in the next week. But for now, to summarize, I have basically got 2 most important suggestions. The first one is people, I think at least people who care to give me feedback are very people like to get more assistance in Python programming. I think that is very legitimate. I will try to reallocate the time a little bit so that when we discuss the algorithms, I'll try to do so with coding examples. Therefore, I hope we have more time in the class for the Python programming. And also, I wanted to remind everybody who wants help, we offer, I think, plenty of time in terms of programming. immediately after this session, I offer 1 hour. Immediately after my hour, Gitas offer another hour. And tomorrow I have an appointment-based office hour as well. You can book the where is that? The office hours from okay, FAQ or okay, embarrassment. I didn't remember where to.
It's there in the spring schedule.
Oh yeah, in the schedule. Yes, yes. I thought I remember I put somewhere obvious. Yes. So those are consultation sessions that you can well look into this, and also I think I have reminded some group of students, but I do not remember. But just let me to remind that again. In our modules, you will find some someone hidden in the small page you might have ignored in those tutorial pages. The tutorial of implementing a linear model, and there is tutorial of implementing ID3 decision trees. For each of the machine learning algorithm I introduced, I will offer you such a tutorial. And those tutorials, although they are jammed in one page, the content is very rich. It's something like 2 to 4 hours length of video tutorial that helps you to implement algorithms from scratch. And after today's introduction to the assignment, you will find those maybe useful. This is for the first thing. The second thing is I get mixed feelings, mostly positively, but some people have some comments about my style of mostly relying on the Blackboard style of delivering the points. I'd like to give you the points while I address those points one by one on the Blackboard. Yeah, but if you find some structured notes is more helpful, I acknowledge this, and I will try my best to give you a more structured notes, make that convenient for you. For today, I have offered, you do not need to check into that right now. You just need to know that there is such a piece of resource here in the online materials. Well, I put an extra, until now, most of the online materials are recordings, but from today, I will try to give you a notebook, also a notebook of what is the take-home points I introduced in class. Okay. You do not need to check into this now, because this will be the notebook I will lively demonstrate in this class. This is just to give you an afternoons. After I have introduced this, you will get this those notes back home. Okay, and in case you want to repeat something, and it also contains it would look like that in this way. So it looks like this way. I will summarize those important points here. Okay. Sure. Well, now I think we are ready to start. As usual, we give a very quick review of what we have learned before. I think my Apple Pencil just dying. Okay. Let me use my mouse for a few minutes. We have gone through 4 sessions in this subject. In the first one, we considered what is machine learning and when to perform machine learning. We think machine learning as software 2.0. We want a machine to program for itself from experience. And for a machine, the experience consists of data. So therefore, there are 3 conditions as a take-home points we learned from the first session. To apply machine learning, we need data. We need to reasonably believe there is some trend or pattern in the data. And so we do not have mathematical or physical interpretation or expression of what we want to program, because if we do, we can just program the machine by ourselves rather than let it to program by itself. In the second session, we consider the 4 elements in machine learning: data, which is a black box that gives us some examples, X to Y, and it is this relationship we consider as the trend we want to model. The most important take-home point from that session is we need to limit our imagination about this relationship. We call this entire possibilities hypotheses. Okay, we need this hypothesis. This hypothesis is a limiting factor. And recall, I have manually created such hypothesis possibilities using a spreadsheet, and I manually selected them. And that selection mechanism, selection operation, is what we call the learning algorithm. And we need a loss criteria to perform the selection. Well, have this framework built. In the third and fourth session, we studied our first machine learning model, family. We considered a very simple construction of the model. We limit ourselves in such a kind of hypothesis that, for each data sample, if you remember, those represent attributes in a data. By attributes, we mean different columns in a data table. We then give each attribute a weight and take the sum of it, and then we will have a number. And we think all the information about the data sample is summarized in this one number, and we do something about this number, such as to compare it to some threshold. If it is less than threshold, we output -1. If it is greater than the threshold, we output +1, and that is called perception. And in the fourth lecture, we acquired a very useful geometric view of this computation. We consider both the data points and the coefficient tuple as 2 vectors. And this operation is just to take the inner product of these 2 vectors. And inner product, if you view them if we view it geometrically, it is just to take the projection from one vector to another one, and the projection is assigned. Then we can compare the sign and the desired output. Okay, given the x, we output something, and then we compare this with the desired output. And then we derive a training algorithm that helps us to adjust the W vector from to this direction or to this direction here. Okay, and this corresponding to select hypothesis in the hypothesis space. So that is what we are up to right now. Okay, I hope my pencil gets better. Are we good to go?
Yes.
Yeah, thank you. Just need a more universal voice. Thank you. So when you're doing your confidence building, I'm I'm writing down the take-home points today. Okay, that's good. What we will study today is our second for the 5th and 6th session. We will study our second machine learning model, ML model 2, decision trees. Okay. As usual, in the first session, we consider what is the decision tree, how it works. In the second session, we consider how to build a decision tree so that it works. And today's take-home points, first, what? This is extremely easy. If, else, branches. I will show you very soon, shortly. Second, what we will get if we view the decision tree from the perspective not from individual, but from data space. So that is let us view how a decision tree works on the entire data. Okay, I have to give you some caveat. Because decision trees works not only on numerical data, it also works when you have categorical attributes, so on and so forth. So data space is perhaps a more abstract notion or concept than we could visualize by drawing pictures. But keep that in mind, but that will not prevent us from understanding decision trees using this view. Okay. Well, and third, that is a tricky one. That is in the middle land of machine learning and programming. Usually when you learn decision trees, many of the textbooks, like I'm reading this ones, tends to ignore this part, but I think it's very important. It's very for beginners. This is an important step to recognize the joint between the theory and the software programming. Here is that how to represent the if else in a form that is admissible for learning. Okay, recall that it's extremely easy to write decision trees out using if-else statements. However, the important part in machine learning, the core of that, is to let a machine do software 2.0, let the machine to program solve, rather than let us to program those if-else. That will, well, defeat the point of doing the machine learning. Then a practical point is how to represent if-else in such a way that machines can freely add or remove or modify or construct those rules. Therefore, it makes a tree-like structure, and that is generated automatically. Okay. And with this, we will very naturally being led to the next investigation. That now I have the I have the format of representing a tree structure. Then how could I construct such a tree from data? Using what material, using what procedure, and in each step in the procedure, what should I test? We try to motivate ourselves into this discussion, and we will tap into a little bit into information theory. Which will be the main point of the next session. Okay. So what is a decision tree? Okay, thank you very much for your polling. So what is a decision tree? That is easy. I think that this window arrangement is just crazy. Takes too much space. Okay, if you cannot view that clearly, let me know. Okay, I try to. Okay, sorry about that. This is a little bit chaotic. So what is the decision tree? I just try to skip that. It's very easy. Well, given a sample of the data, by a sample of the data, I mean, so here is your data table, and looking into one sample in the table or one row of the table. And then we consider the data sample as a collection of information, right? So let's call that xi, okay. And look at this xi refers to the ith row, and it has multiple attributes. And we want to make some decision about xi to predict some y. Okay, what is this? And a decision tree works in such a way, it make a judgment about individual attributes of those sample, like if see xi's second or maybe, well, this is a third attribute is less than 1.0, then I will just let the prediction to be +1. Otherwise, maybe I let the prediction to be -1. And of course, this is a very simple rule. We can build more complicated rules, such as when we enter this else branch. See, this is xi, and I have made decisions about xi on its second or the third attribute. Okay, and we compare that if it is greater or less than 1.0, and when yes, we have arrived something. We know we might want to make further judgment, such as, look, how about let's compare the second attribute with something else and make further decisions, so on and so forth. So this is a direct map of a tree structure and if-else statements. Right? So that is just our first point. I don't think we have much to talk about this. It's very intuitive. What is interesting is how would such a rule give us a picture on the data space? To understand that, please try to recall what do we mean by applying a hypothesis on a data space. We start by reviewing what we have applied, that when we apply the perception on the data space. Look at here. By the way, if you want to join, you can join the project. It's the same. I just add a new notebook in our project, okay? So I started here. What's wrong with my project? E. Maybe the virtual machine has an issue. Let me restart it. Hopefully that runs well. Okay, never mind. Let me use another notebook. It's in the online materials and this one. Let me open that in playground mode. So now you can see that the platform does not matter too much. We use only basic functions of Python. So whatever environment you can get your hands on, it's okay. Well, please recall this picture of applying a linear model and then do a classification on the data space. So at each point, we generate a number and use this number to represent, use a color to represent this number, and make decisions about the location. Each location in the data space represent a potential data point, of course. So this is our classification rule, how that look like on a data space, right? Now, in decision trees, we do not have such an intermediate representation of the information of the data. We don't have that color. We make decisions from our if-else statement directly. Okay, so let's try this. I have implemented a visualizer to show the class directly. So I use this one. Let me remove those complicated things. Okay, I try to remove that. Okay, and I try to keep that simple in the previous notebook and give this to you as a take home notes. Anyway, so what I'm doing is in this classifier, given the data table. So this is a table of data, and this for loop look into each sample in the table, and what it should do is to give a value of the corresponding prediction. Okay, let's try to implement this. So for example, let's do bring that one. Which means I do not do a classification at all. I just give everything a positive class and see what we have. We will get. Of course, this is non-interesting. So let's do another branded one. If numpy.random.rand is greater than 0.5, otherwise I make it to be -1. Okay, let's make the if else more explicit. If a random number is this one. Okay, if my random number is greater than 0.5, then I will predict it as +1. Otherwise, I will predict it as -1. Of course, this is a no-brainer, and this won't be very helpful. But just let's see how classification goes. Okay, look, this is a very random pattern. Well, now let us do something more useful. Then we may recall what we have done in the spreadsheet. Why not let us try to make a more informative decision according to what is available to us. That is the information in XI, if you remember my drawing. Okay, please be please distinguish the superscript, those index things. Here I refer to the first and the second attribute, but the I here refers to the I data sample. Okay, so for the I data sample, it has the first attribute and it has the second attribute. Let's consider the first attribute, this one. Okay, compare that maybe 5 to 5.5. Let's try a little bit here, maybe 5.51. Let's do that. So now instead of using a random number, no, I don't do this silly thing. Let's do some informative thing. for this xi, look at this one. Okay, 5.5, 1 maybe. Okay, let's try. Look, these things start looking interesting, right? Okay, we can do more. We can as we have introduced, we can do nested, which means one if else inside the branch of another if else. We make a decision here. We can make a decision here. Okay, maybe on the left hand side, we will find if I just color everything here as purple, that won't be a good idea. How about we cut another line here and make this part purple and this part yellow? Let's just do this. So in the else part, we do another if xi, let's do xi1, so which means refers to this one, and compare that with maybe 2.75. So in this case, when it's greater than 2.75, we will predict it as -1. Otherwise, we predict it as +1. Let's do this and see how it goes. See? It definitely start agreeing better with what we have observed. Okay, I have a question asking about what is shape 0. Okay, shape 0 is a shape of an array refers to the number of rows here and the number of columns here. Shape 0 is just the number of rows here. Okay. Simple app.shape 0. It has 100 samples here. Now, it is very intuitive to try yourself. Maybe in this branch, in the right-hand side, we can also do a split. For example, we can do a split maybe here. Okay, and this one is let's do 3.55. How about let's try this? Okay, well, if xi1 is greater than 3.55, then we will let it to be -1. Only when it is less than that, the prediction will be the +1. Okay, so let's run that. Where's my running? Okay. Uh-oh. Oh, sorry, not +1, it's -1. Let's run again. Okay, now you see that we have manually built a decision tree using if and else statement like that, and we have studied how a decision tree works on a data space. So that basically is what a decision tree model does. Only with one caveat, as I have mentioned before. Here, in those parts, sometimes you do not. Sorry, not sometimes. This is not limited to numerical values, as long as there is information in the corresponding data attributes that allows us to take information about that sample. It is okay. It's not necessary to be numerical. You can see maybe this attribute is like a male or a female. You do not compare to a number, okay? Or maybe in this attributes that refers to the favorite sport is rugby or something else, maybe swimming. So it depends on the data. And the tree construction and the construction and prediction algorithm have no requirement that this is numerical. This is the caveat here. Anyway, here is how a decision tree works on individual data sample and how this working mechanism look on the entire data space. Okay. Oh, sorry. Sharing. Now we are going to address our next question, which is how could we represent those if-else construction in a way that the computer can program itself into such a logic flow? Equivalently, of course, we do not explicitly let the computer write a program like that for itself, but the information processing logic flow will remain the same in this way. Okay. Okay, it seems that we are good to go. Yes, let's continue. Well, this part just to show you the answer. However, I will show you the construction of this from scratch. Okay. And after that, I will give everybody 10 minutes to reflect, and you can practice by yourself. I talk through this quickly, and you have the opportunity to open the notebook and try by yourself. And the notebook link is in our online materials here. Okay. What we will do is to create a template of we will create a template of objects. Let's call that tree node. A tree node is something. Where is that? Maybe. Okay, that will work a little bit smoother. You can see my screen split nicely, right? Okay, and we have ticked this, and now we're on this. So A tree node will consider this. Okay, we are making a template of that, and we will consider all the working conditions of this object. The first one is the easy one. If there is a decision associated with that, which means our brain dead situation, not brain dead situation, look like that. In the 10th line, there, in the 12th line, or this line, at this point, you do not do anything more. We have a decision that has been made. We just return this decision. Okay. I construct that in a conventional way. Okay. I put an I here to represent this is working on a specific data sample. Of course, we can extend that to work on a group of data. Okay, so. Or maybe we can just put that on a group of data and copy this this here. Okay, sorry. Let's do the XI one. This is easier to understand. Okay. The first one, in the first step, let's consider if there is a decision. Then I can return. Okay. Of course, to implement this situation, this mechanism, we need an attribute called decision linked to this data. Sorry, associated to this object. Okay, I put it here in the initialization. We allocate a decision here. Well, on the other hand, when the situation is more complicated, which means we have not arrived at the situation where we can make a decision, we need to perform further steps according to some information in that particular data sample. Okay, so what we can do is to take the value of the xi from the attribute to check. Okay, and now we take that value, we check that value. If this value is greater than self-dot-threshold, I remind you, this is an implementation that works for numerical data again. Okay, in some of the example, including the example which I give you in the tutorials, we consider the categorical some data. In that case, you do not compare that with a threshold. You can compare that with all the possible values, such as male, female, or different kind of sports, different kind of weather conditions, things like that. Okay, but now we use a threshold to create two branches for numerical value, greater than or less or equal to. Okay, if that is this part, what can we do? We will enter in this branch. And the elegance of the designs here, now we no longer do further processing using this node. Why? Because the design is looking into A2 check. Then this one or this one. And that is to delegate to child. Because under this one, we will have more nodes and the decision making will be given to those. You just need to give the job to others to finish. And you can just return whatever is returned by the children. Okay. Then what we do is to call the children self.children. And this children is greater than. We call that, and the children will have the predict as well. And we will let the children to predict on the same data, and we return what the children gives back to us. On the other hand, we will return less than, maybe less or equal, but that doesn't matter too much. So anyway, okay. Then to support this operation, we will create some attributes for this data in this data structure. Of course, we will have self attribute to check, which is none in the construction. We just need a placeholder for this piece of information. Threshold, which is none, and self dot. And now we have the children part, and I give it an empty dictionary, which represent the two linked nodes with this parent node. Okay. Now we can start playing with that. So let's create one of the tree node. Okay, and we can define a classifier in this way, in the same format as that. We use tree node. Okay, and we give the maybe okay. I'm lazy. I will just use tree node inside this function, which is not a good practice, but kind of convenient to realize. Please keep that in mind. Where is this? And for the decision making, I will rely on my tree node. Okay, predict I is a tree node dot predict. Well, this si. Okay, let's test that. First, let's make the simplest possible test tree. It has no children and it has only one decision. Let's see what we have. Okay, not surprisingly, we go back to the situation where we only have one decision. Of course, we can make it more complicated. For example, in this case, we will create two branches, tree left, another tree node, and tree right, another tree node, right, left and right. What's that? Annotate, and with spotlight here. Okay, left and right, I create these two. Well, in the left part, let's return -1. So decision -1 and it's +1. Well, then we need to remove the decision from the previous tree node because it has no decision right now. It needs to delegate the samples to its keys. Okay, what we need to do is to let it to judge on some attribute. So here is the attribute to check, the values attribute, and we choose a threshold. Let to be 5.5. Okay. Now we link. Now we do the link. The left-hand side less than. Let it to be. We need to do the link after we have created those guys. Okay. Right? Okay, let's run this. Uh-oh. Good, sorry. Greater than. Not right than. Now look, we have start building the tree structure. Well, maybe consider the first split on the left-hand side. Okay. Similarly, we remove that decision. We do further check. We just copy this here because that will look very similar. Okay, this attribute to check is attribute 1. This attribute, right? So we change that to 1. And the threshold will be maybe 2.75. Okay. Excuse me. Well, and also we create here. We create a 1, 2. Okay, similarly, I'm doing the link, but this link will link this guy with its L1 and L2. Okay, I'm creating the link here. So L1, L2, right? Let's test. What? Okay, I forgot to put the threshold here. Which threshold I haven't put? If greater than the threshold. Did I misspell that? Give me a sec. So that is what happens when you try to do live programming. Sometimes that happens. So that threshold is this, and well, split wrong at line 11 and 12, 13. Thank you very much. Let me have a look. Decision. Look, that is what happens for a grammarly loose language. When it's C++, it will complain. But now, things happens is I didn't give it the decision, and the decision will automatically set to none. And because the decision is set to none, it's try to find the branch, and it cannot find the branch, and then it complain for a irrelevant issue. But anyway, now it's okay. Oh, look, we are building that. Okay, so given this example, I'd like to give you maybe, I think you need something like 5 to 10 minutes to get your hands on to practice. And if you have questions, please, because of the computational resource limit, please try on Colab. And if you have questions, ask in the chat box, and we will. Maybe I can help you in the where is that? In this, I really don't know what's going on in this notebook. Okay. Anyway, let's try.
Sorry, Jim, can I ask a question?
Yeah.
Can you talk more about so for one of the like parameters or attributes of the constructor, it's attribute to check. Can you talk about how, like, why do you assign 0 to the root node?
That's one. Yeah. 0 and 1, right?
The one above, the tn dot attribute to check for the root nodes.
The second, this one.
Yeah.
Okay. Exactly.
Why do you assign 0 to that? But 1
that's yeah. So okay, let's first see what is that. What that means, I'm checking this attribute, the attribute representing the horizontal axis. Okay, that is a part of the question, but I think your question is more about why I need to check that. Okay. Well, I do not know if you remember when I introduced the perception, when people asked me, why you have chosen the W1 and W2. I said, oh, just a random. That is a very good motivation because shortly and in the next session, we will start to learn why we have chosen this attribute as a criteria. Okay, there are different ways of choosing those attributes, and perhaps if you remember one thing or two from the introductory to data analytics, the selection criteria could be like information gain or Gini index, whatever, which helps you to purify the distribution of the y part after we have make a decision about the particular attribute. We can make a decision about this attribute, and after the decision has been made, we will now have two groups of samples, okay? And we can measure the purity of the label distribution in the two groups and take a weighted sum. If the weighted sum shows that the purity of the distribution of the y improves from the original distribution, that means our decision making helps us to gain information about the answer to the particular sample. Okay, that is a general guideline. We will consider the details in the following discussion about a decision tree.
Right. Can I have a following question? So since you were explaining with the diagram, so with the value 0 that you assign it to the attribute to check represents the x-axis and the 1 represents to the y-axis?
Yeah.
The value. The 0 means
okay. No.
y in the diagram?
No. Here it is. I'm showing that. This is a misnomer. This is a very common misnomer in this field.
Right.
Like this way. This is x0. This is x1.
1, okay.
x1. And y, what is y? Y is color. Those colors represent the y.
Okay. So 0 means x0 and 1, the value 0 of the attribute to check means the x0 and value 1 of the attribute to check means x1.
Yes.
All right.
And you can see from the other example of our classes. And
All right.
Look, sometimes I use different name. The split feature name, which is the yeah. So in that data, the columns have name.
Yep.
In that data, in the data we just use the columns does not have name. They are column 0, column 1, column 2. But this is column outlook, column temperature. Wow, it's just a name of the column.
Okay. Yeah.
So that's a good question, and I think that helps people understand.
Yeah, you helped me. Thank you. Thank you so much.
Please practice for a little while. Bear with me some. I'm grabbing some water. Okay, talk to you soon. Okay. In the meanwhile, if you have questions, you can ask me. And yes, of course, please.
Hey June, can you just scroll up for a little second on the collab?
On the collab, what?
Yeah, I just want to see the top cell, the one.
Top cell.
No, just that was good. Just a bit down. So the one where we implemented the predict function.
This one.
Yeah, this one here. Thanks.
Well, I have to say, this is not the optimal implementation, of course. Why? Look, because the processing of this could apply just to all the data in such a way that, look here. By the way, you do not need to watch on my computer. You have the link to the notebook and you can open that on your computer. Okay, so look, now we have to make a prediction function that helps us to loop over all the data samples and give the sample to the tree node to do the prediction. This is not how a real decision tree works. It is a very natural, which is very awful and also efficient to just provide decision tree all the data, let the decision tree to do its internal job about the data. So we could give the entire data table to the tree and let the tree work by itself. So the prediction here is not very efficient. Okay, if we are good now, let's talk a little bit about the information theory part before we go to the quiz and talk about the assignment. If we do not have enough time to finish talking the assignment, I will keep talking it in the next session. Don't worry, I know that is important. Well, as the previous question suggests, I'm very happy that in both this decision tree model and the perception model, we have successfully motivated people enough to ask why you have built such a model. That is a really good question, and now we're addressing that. We will build the model automatically, let the machine to build the model out of the data. We will not choose, okay, 0 is the column you're looking into, and 5.51 is the threshold. You will split the data. And in the next step on the left side, 1 is the attribute you are looking into, and what number is the threshold. We want those this meta decision making to be automatic. That is the essence of machine learning, right? Automatic according to data, so that the built rules is agreeing with our data. So a natural thought about this is working this way. Well, now we are given the data, and the essence of the data, the important part of the data will be well, actually, I do not see the important part of the data. The ultimately interested piece of information of the data will be the classes, right? Now consider if the data is given in maybe some container or whatever, a bag maybe. So we are interested in the attributes of the data only because in this bag of data, the classes are mixed. There are more than one classes in the data. So we need to distinguish, right? It is, think about this way. If you are a fisherman and you want to catch some sea creatures for maybe food or commercial usage, however, there are some well, environment protection regulation rules. So we cannot just catch whatever we could catch from the water. We need to protect some creatures we do not need to, we cannot catch them. In this case, we need to create different kind of fish nets. We need different kind of technology. We need different kind of operations to do the fishing. Okay. On the other hand, alternatively, if you know for sure in some water body, or you are operate in some agriculture land, sorry, not land, a pond, maybe something that is cultivated by people, so much so that you are sure whatever you want to catch, you can only catch one kind of well, creature, maybe fish, that you want, which means you only have the desired class, you do not have to distinguish, then there is no need to look into the other attribute of the samples in your net. So that is the logic. If you accept that, so now we can move our focus on the mixture of the classes in our net, right? And the key point here is we want to create some mechanism by applying that could split the population in our net in two parts, and in each of the part, the classes are pure. The class distribution are purer than the previous one, so that we can make decisions about them. So that is the intuition of building the trees. We're looking for data attributes and using that attributes to split the samples, the data samples, into subpopulations. And in those subpopulations, the distribution of the target value is purer than the original distribution. Yes, that is the general principle. To implement that, in this starting point, we introduce the very first step is that we need some kind of measurement about how pure it is for a distribution. I think everyone can agree that if I have some samples like that, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, sorry. What's wrong with my, okay, 1 0 0 0 0 0. Okay, and the other one 1 0 1 1 1 0 0 0 1 0 1 1 0 0 1. In which string you think the distribution between 0 and 1s are pure? So probably you think this is purer than this one, right? Okay, now in the next step, we will try to introduce a systematical way of measuring, of mathematically talking about what a population makes a population purer than the other one. And the story behind that is a very clever construction. What makes a distribution purer? Think about that. If now we kind of cover both distributions into a black box, okay, and now one guy is trying to take a sample from the black box, and maybe this is Bob. He wants to tell Alice about zeros and ones of the sample. And Bob wants to talk as less as possible about the information. So the minimum length of the communication, actually I should say the minimum length of the average message of this communication is what we want to define as how pure of the distribution is. Think about one situation. If both Alice and Bob knows that it is 100%, the black box will give 0, and no ones is ever possible. So in this case, on average, how many, maybe let's call that bits, needs the, Bob needs to tell Alice about the outcome of the sampling? Do you have an idea? It is like, if I want to tell everybody about my observation of on the east side or the west side, the sun rises every day for maybe 30 days. How much information I need to communicate with you? If we need to pay, for example, for a very expensive internet, you could argue that 0, right? Because those kind of events, we know for certain that kind of events contains very little information. Sorry, what I should say is, should have said is the outcome of those certain events bears very little information, because the structure, the outcome of those are very well known even before we do any sampling. On the other hand, if I'm going to telling you the result of maybe flipping a coin, a fair coin, of course, for 30 times, so probably I need to tell you 30 bits. There is no way to save from this very random event. So the outcome of this chaotic event bears a lot of information. Once the outcome comes, it tells you something about that, which we did not know before. Okay, from this principle, we will define the measurement of information, which is called entropy. Okay, I have said this is the fourth point today. Okay, we will delay the definition of entropy in the next session. Okay. So today's quiz is simple. Let's quickly go through this, and after the quiz, I will talk about the assignment 2. Okay. So there are 3 questions as usual. Consider the question 1. Consider the statement about decision tree predictors. Which do you agree? The first one is that more decision nodes leads to more complex predictor tend to be more accurate when applied on the test data. All the previous statements are correct. More nodes leads to more complex. Look, this is more complex than this is more complex than this one. Okay, if you build more nodes, you can cut the space finer and finer. However, there is a mistake, and it tends to be more accurate when applied on the test data. That is wrong. If we build too many nodes in that, we will actually create a tree that is not only be able to memorize the data, the correspondence between the data and the target value, but also be able to memorize the noises, disruptions in the data. So that is basically asking about the overfitting thing. You by now you can get the theme of this subject. I constantly remind us, machine learning is a way of selecting hypotheses from data statistically. It's not something like a deductive learning. It's not something like built from principles. We learn from statistical rules. So overfitting is some danger that is always looming there. So we need to be aware of that very well. The second one is correct. To achieve the same classification on the training dataset, a tree of less questions, less nodes is more preferable. So the second question asks about the information we have discussed before. The first one, state 1, the outcome of half-half event contains more information than bears more information than an outcome of a very skewed experiment. So this is true. Second one, for an experiment of 2 possible outcomes, and these 2 possible outcomes, actually not 2 possible outcomes, there's only one is possible, the other one is impossible, contains no information at all. This is also true, as we have discussed. Okay, so both statements are true. Question number 3, consider the statements about the decision tree predictors. What do you agree? Well, the correct answer is each leaf node. Leaf node means the node at those locations, there's no further branches to make that will make a prediction of the target corresponding to the code is here. Predict. If the decision is not known, which means there is a decision, return the decision. And that means this is a leaf node. Otherwise, it will delegate the processing to its children. The other three are wrong understandings. You can read later, such as misunderstanding of the number of nodes and the number of training samples and number of nodes of the attributes. Of course, you can use or you can miss some attributes in the decision making. For example, we can use only one attribute to do the decision making rather than use two, or we can repeatedly use one, such as we cut this way and we cut it this way again. Yeah, so basically you can have a quick glance of those misunderstandings. Quickly, question 1, fewer nodes better if it agrees with the training data. Question number 2, both statements are true. Half event contains a half event. This outcome tells you more about an event. There is some very impossible and very likely outcome. Step 2, if an event is certain, then the event that happens, this fact does not give you information. This is true as well. Question number 3, the leaf node in the tree gives you the decision about the target. Okay. Well, in the next I got a question, Jackman. Why less questions? Jackman, less questions represent less complex or simpler predictor. Simpler predictor is more preferable. Okay. If you have less questions, such as that, if you only ask maybe 1, 2, 3 questions, you have something like that. If you have a lot of more questions, you can do something like a jigsaw puzzle on your data space, which tends to make more complex predictors, and that is less preferable. Okay, we can look at excuse me. We can look at the implementation techniques details later after the session. So while everybody is here, let's share some discussion about the assignment 2. So there is I've just put the assignment 2 here. It is to let you to implement a machine learning model and do the and do the training and test the learned model on a data set. So please read the specifications. Some important part I want to address is the algorithm needs to be implemented from scratch. So what does that mean is if you import a tree classifier from scikit-learn and create an object of the classifier and apply the classifier to a set of data, that does not count as implementing the algorithm. You need to implement the classifier by yourself. So please read the specifications. For the interactive time, let's talk about let me clarify some very often asked questions. Here is an example specifying, showing how those specifications particularly means. Okay. The format, what does it mean by discussing the code and referring clearly referring to the implementation, and how can you provide us your implementation, stuff like that. Please read those specifications. Okay, and I hope if in the next lecture we still have more time, I can talk about this. Here are some very often asked questions, and I give you some example of good and bad submission. Okay. So here first a good example. Bear in mind, in that example, we have marked the assignment based on 100 points, but the rubrics on the site, this rubrics is given based on 50 points. So there is a weighted difference. Don't worry about that. Okay. Look, the title is according to specification. It's good, informative. He provided a link. The link is both collectible and is given in plain text. That is to prevent, in some cases, because of some of the security setting of PDF processors, it will remove the clickable link. Please do not just put a link and a hyper URL, text URL in the link. When maybe in the submission system, your link has been removed, then we will not be able to find your implementation. So the link has a specification there. And I have checked the implementation that has been implemented very carefully. Let me try to show that. When we mark your assignment, what we will do is we will just click this run all. Okay. There is what is needed from your side is, of course, prevent yourself having little bugs or some incorrectness, glitches, whatever. Therefore, we cannot run till we see the result, and then you lose marks. Okay, and importantly, if you are going to use data that is outside whatever provided by scikit-learn or standard libraries, you need, it is the student's side, we need to see some like code that you can see download. No, not this. There's a code snippets. you can download files. No, sorry, maybe open files from something, whatever. You need to put a piece of code that let this notebook access the data you will use. That is to see if you use some data that is outside standard libraries. So we will just click run all, and we will not try to download data by ourselves, do something. If you use data outside the standard library, please prepare the data in your notebook. Okay. We will read into this, but we will not check the duplication here. You are allowed to reuse the tutorial code I provided you, the class notebooks, the notes I'm using in class, everything you can use. We will not check duplication here. We understand there are only limited ways to implement some very mathematically strict algorithm. We don't check duplications here. Okay, you can reuse the code from the internet. It is okay. Okay, but it will be very helpful if you can provide your comments on the code. You provide a good like a function signature, well, specification, and provides anyway information about how to read into your code. So if you have put a lot of efforts of implementing that thing from scratch, you probably will like us to mark that according to this true merit. Okay. Well, mainly we will try to understand your code from the report, and we will read through your report very carefully. Like the introduction part, you will see the specification in the document, in the rubrics, and the algorithm. And I have found the highlight of this submission is that it optionally, it implements one thing that I haven't mentioned in the class. It deals with both continuous, which is numerical, and discrete features in the implementation, and I have made that clear. So the implementation is so this is improvement comments. I think that it's good enough to oh, where is that? Meeting all requirements, and I don't remember if I have put that in the comments, but I remember that submission is very impressive. It deals with both the continuous and the discrete situations. It's very good. And look, in the discussion, it talks about the definition of the mathematical definition of the concept and how the concept is mapped in his code here, and his understanding of that, and his consideration of the computational issues, stuff like that. Okay. And in the evaluation, so all these, the students have discussed the working, how his code works. You do not need to because this is a machine learning course. This is not a data analytics. This is not focused on pre-processing data, stuff like that. We focus on the analytics part of building models. Okay, so we are allowed to use toy data such as iris data, such as whatever comes with the scikit-learn library, and we can use the pre-processing procedures from the library. Look at this, like that student have used provided methods from pandas library to process the data. So you do not need to implement the data pre-processing and preparation from scratch. No, you can use whatever library provided you to prepare the data. Okay, it would be good if you remember to split the data into training and test, and use the training to train the model, and use the test to show that, okay, my trained model actually works. Okay, and please do some reflection on the conclusion. So this is a full mark submission. As I said, we do not check duplication in the code, but we do check duplication in the report. Here are some examples. This is, well, I won't say that is a good example. This is a borderline example. Look at this submission. There are multiple repeated wording of the concept. Okay, although we understand that for some of the wording is inevitably repetitive, but try your best to well, avoid these blocks of repetition. For those, this student take a very tricky way. It placed very dangerously. He tried to use one source of quotation and try to quote everything he copied into the report. I probably won't file a misconduct report on such thing, but definitely we all understand what he's doing. So this kind of report won't get good grade. Okay, and if you are not careful enough, maybe for one sentence or some piece of discussion, you forget to make this quotation, and then your report will get 0 mark. Here is a really bad example. Okay. So we don't accept argument that this is the definition of decision tree I copied from Wikipedia. No, you probably will not need to copy the definition of a decision tree. You are there is a lot of ways to introduce the decision tree using your own words. We don't accept this kind of whole sentence or whole paragraph copying. Okay, this will receive 0 mark, and I will file a misconduct report on this kind of submissions. Don't do this. Okay, if you still have, let me have a look at any important points. Okay, I think I have addressed the most of the main misunderstanding of the assignment. Those are the mostly asked questions from previous years. Of course, there are a lot of details you can check from the specification. This sample document can be downloaded from the assignment document. It's here, example.pdf. But I won't provide you the example submissions. Okay. Good. I think we are 5 minutes. Before we wrap up, we have sorry. We have 5 more minutes. Before we wrap up, let me bring everybody into the discussion we will have in the next lecture. This is not a good rendering. Okay, look at this. For the information theory, so this is what I'm talking about as a preview into the points we have discussed in the class. Sorry, we will continue to discuss in the next class. It's about measuring the information. We have discussed that more unpredictable event will give us more information if we have an outcome of that event. So how to formally define information? Basically, we will introduce a concept called entropy. And entropy is usually, well, don't be confused, usually represented using this capital H. When I refer to the hypothesis, I usually use this calligraphic H, and this is capital H, okay? So this capital H accepts an object that represents a distribution. What is the object that represents distribution? For example, you can have something like 1/6, 1/2, 1/3. You can have an object that is 1/10, 1/10, 1/10, 1/10. There are 10 of that. So basically, you can understand that loosely like a histogram. A histograph represents the likelihood that maybe different events happen. Okay, and this capital H accepts such an object and returns us a number. And this number represents the information of this setting up of the stochastic random system. It follows 3 rules. Okay, so first, it's continuous with those numbers here, which means if you have 0.1, 0.5, 0.4, this will very similar to 0.101, 0.499, 0.4. Second, the chaotic measurement, the information of one outcome varies increase with the randomness, which means if you have each Okay, that is smaller than go so on and so forth. And the third one is a branched sequential choice principle, which we will introduce in the next session. Okay, so this is just a preview. Before you go, please let me know how the session goes with you. And if you have more questions, you can stay for another hour. I will talk about, maybe we can talk about the implementation, or maybe you can join us to play with the code. And if you have questions about the assignment, you can also let me know.
Hi, Jing.
Hello.
What does the 1, 6, 1, 2, and 1, 3 mean? Are they like probabilities?
Yes, yes. This is, oh, sorry, 1/6. So if you have 3 possibilities, happens with maybe 1/6, 1/3, 1/2.
So when you giving this example, it's like a list of 3 possible incidents with the different probabilities.
Yes.
Okay.
In our discussion, we usually consider only 2 possibilities, because to simplify things, we mostly consider the 2-class classification in this subject. So our possibilities is usually something like 0.55 versus 0.45. We consider these distributions. This is pretty simple.
Okay. Can you just scroll the page up a little bit, please?
This page?
Yes.
I have a question. So the 1/6, 1/2, these probabilities of what? Oh, of whatever. When we consider the information, for example, if you have some confidence that maybe 3 teams will compete to get some championship, so you will see the championship contains some amount of information. On the other hand, you may have some possible outcomes of, say, there is maybe one COVID patient will have been infected by some kind of variant of the virus, different types of the variant. So if that possibility is the same as the possibility of teams competing for the championship, well, from the information point of view, that makes no difference. So whatever fall, as long as the possibilities keeps the same, we will see the information are the same, is the same. Think that way. If you have a deck of poker card, okay, well, you could talk about well, if we play poker, well, I have some kind of possibility of have a full house or whatever, and you try to discuss statistically different outcomes or events, whatever, regarding the poker card. Well, that does not matter if you have changed the printing of my poker card. You can change the card into printing maybe the spade of using a different shape, of writing different text on that, as long as the composition of different cards and their outcome possibility keeps the same. That does not change the nature of the discussion about the statistics of the card. I have a question, and the question is about what is a hypothesis? A hypothesis refers to a possible link between the X and the Y we would like to consider in the learning framework. Where is my... Okay. I think one hypothesis may be of very little interest. To get a comprehensive point of view, you're probably better off consider a set of hypotheses. Like in our, a linear classification models, our hypotheses, or alternatively, you can, well, let's talk about it in this way. I think that is, politically incorrectness. If you are a person with a prerogative, you think you want to judge people according to their colors of skin or their sex or whatever. This is your bias towards people. Okay, if you are like a bank manager, a good bank manager will judge people according to their financial situations. Like, given a customer, I look at the customer's previous credit record, when it's the last time the customer has been like being late in repaying debts or never happens, things like that. Maybe another bank manager is a bad one. He try to judge the customer according to the sex, the race, stuff like that. Both bank managers, they have their own hypothesis set. The hypothesizes, they guess whether in future a customer will bring them a profit or make them at a loss by looking into some attributes of the customers. But in both ways, they will have some, well, in a sense, baseless and not very well established principle, non-principled rules to judge people, to judge the customer, and those set of things is called a hypothesis. And in machine learning, of course, we don't consider whether it's correct or not to do so, but just as a methodology, we think we have a collection of such hypotheses, and we want to use the data to select one particular fit to what we have observed, and that's called learning. Okay. One thing to be mentioned, to be noticed is that selecting the hypothesis set itself is an activity that is above learning, that happens before the learning. We don't learn the hypothesis set. Given the set, we learn something within that. Okay.
So, sir, it's like our own assumption, right? Let's say someone living expense is more than $5,000 a month. He must be rich. It's kind of a hypothesis, right?
It kind of, but you think that way. Your hypothesis, you think that way, to assess someone financially, we look at his or her bank transactions. So we will do something about his bank transactions, and that is my entire set of hypotheses. Alternatively, maybe you can see, look, to assess someone financially, we look at maybe variable, whether the one possess a property, whether the one has a vehicle, stuff like that. It's just like one layer up in abstraction of your thought. You think we need to check those pieces of information. That is your hypothesis set. You need only to determine this one. You don't determine, okay, we compare the person's last year's income, maybe times a factor of 0.5, and compare that with that guy's outstanding debt. If it is greater than something, we arrive some conclusion. No, that is not machine learning. That is your programming, your own programming of the bank computer. Machine learning is you tell the computer, look at those attributes and form some rules by yourself.
Thank you so much, sir.
So do you mean that the humans playing the role that we give the computer, the machine, a direction, and provide the right data set that the machine should look at?
Yeah, exactly. Yeah. Good.
Okay.
Yeah, that's good understanding. Of course, well, that said, we talk about only, well, entry-level techniques in this large field. if you are interested, there are a lot of different paradigms, which means that there are lots of different frameworks in which we can perform learning. It's not always possible or necessary or a good idea to learn. Like if I observe something, I immediately produce something, and I have a lot of pairs of such, and then I learn from those collection of pairs. No, think about autonomous driving. Well, usually people won't have collections of data of such as okay, my maybe screenshot shot camera takes images, and at the moment the camera has observed a situation like that, the driver should turn the wheels in this way, or it will hit the accelerator or hit the brake. You usually do not have this kind of operational data. Okay, so people often try to recognize objects and then manually construct the driving decisions, control signals from the perception, from the perceived environment. But that there are different approaches to this. Okay. There's a lot of interesting thing happens when people try to formulate a task into one that could be addressed by a learning framework. For example, you can write a machine. You write a model, which I did for fun last year, to mimic how Shakespeare writes plays. In that, what is your observation X? Okay, the observation X is the words that has already been generated, or at the beginning you can have a meta word, which means begin. Okay, and what is the prediction? Okay, the prediction is a huge one. The prediction would be 60,000 ways probability distribution, predicts the most probable English word in the next to be generated in the next step. Okay, then you repeat this procedure multiple times. Well, kind of randomly generate an article that written like by Shakespeare.
So, I have another question if other students don't have any more questions. In the lectures, I don't understand how you calculate the average questions for uneven probabilities. I saw the numbers like 0.5 into 1 and 0.25 into 2, etc. How do we get that number?
Can you? I didn't get that quite clearly. So, which part you refer to?
It was module 3.2. So it's in the YouTube video. Is where we calculate average questions for uneven probabilities.
For even probabilities.
Yeah, uneven probabilities.
Yeah.
Yeah. So how do we get those numbers?
For example, by even probabilities, maybe
it's a Marvel.
things like that. This is just an example. You want to compute the entropy of this?
Actually, my question is more simple. It is not it's not coding actually, sir. It is about like a simple calculation. How to calculate average questions needed to solve an even probabilities.
Understand. Yeah, right.
Yeah.
For
So
that
sorry.
part,
So
yeah,
sorry. My bad.
For that part, I will address in the next lecture. To get a quick viewpoint, it's like that. Let me ask you. If, for example, I have two objects like that, I'm not sure if I kind of lost my camera. Where is that? Where is me? Okay, I'm here. Okay, I'm here.
But I can see you.
Okay, you can see me. That is good. So look, if I am two objects, okay, and I tell you, maybe let's see, one of it is heavier and the other is so one is heavier and the other is not is standard. I just see one of these is heavier than standard. So if I give you a scale and let you to weigh the objects, how many times you need to weigh them to tell me which is heavier?
Just one.
One, yes, okay. Then I do not have that many airports, but think if I have 4 objects, how many times you need to weigh?
Maybe 3.
No, be clever. You can weigh these 2, and if this is heavier, remove that and weigh these 2. Right?
Yep.
So you only need to weigh 2 times rather than 3. Okay. Think if I'm letting you to distinguish 8 objects, how many times you need to weigh?
4.
No.
No,
You weigh, yeah, 1, 2, 3.
I see.
Okay. So in this line of thought, you can think for every one bit of description, we can distinguish twice as many different situations, right?
Yep.
Okay, I have 1 question, I can distinguish 2 situations. I have 2 situations, I can distinguish 4. I have 3 questions, I can distinguish
8.
Okay, so of course, this only works with 1, 2, 4, 8, 16, 32, stuff like that. But you can generate this a little bit into more general situation, like you have 10 situations, you have 20 situations. Therefore, you calculate the bits needs to describe that situation using log. Basically log 2. Okay. So you can see if you do 1. If you want to do a little bit more, okay. See, this will need 16 questions to split these situations.
Oh, I see. Thank you so much.
Okay.
Oh, hi, Professor. Yes, may I ask a question?
Yeah, please.
Yeah, regarding the assignment 2, so could you provide us a list of algorithm we may implement? Yeah, a list of. Yeah, because when I read the assignment description, it's quite vague. We can search any algorithm we can use, but I'm not sure if I implement like simple linear regression. Is it okay or?
It's okay. It's okay as long as you implement by yourself and discuss it in a report. A linear regression, if you try to implement that, clearly, it is not that simple, to be honest.
Okay.
Yeah.
Yeah. So that's why I wish you can provide some maybe feasible or at our level which we request.
I provided 4 algorithm tutorials: perception, decision trees, ensemble, ADA boost, and neural networks. I provide 4 tutorials.
Okay.
If you wanted to implement something else, I think it's also okay, because as far as I know, the perception and the decision trees, maybe they are the simplest models. If you want to implement something else, you must do something more complicated than required.
Okay. Cool. All right. So right now we have taught decision tree and perception models. So the other 2 we will teach in next 2 weeks, or?
Oh, that's a good question.
Because the assignment due on the first week of October. So
okay, I'll try. That is a good point. Okay, I will try to publish the materials for the remaining sections soon. Yeah, we have passed the census date. I think it's a good time to publish everything. Yeah, good.
Thank you very much.
So we are not limited to only the decision tree module to do the assignment, right?
No, you are not. You can do any machine learning model that, as long as you implement that from scratch.
Okay. So, did we limit our tasks? Are we required to build a classifier or just a regression module?
You can do either. You can do both classifier. You can either is okay. Either is okay.
Okay.
Maybe regression one needs more math.
Okay.
Yeah, but it's simpler to implement when it comes to programming. But it needs more mathematical reasoning, a little bit more mathematical reasoning. It's okay. It's okay.
Okay, thank you.
Okay. So if there's no questions, maybe we wrap up here. And if you need more help, you can come to guitar session after a cookie or 2.
So I have some suggestion. It would be really useful if you recommend some math books regarding data science, mathematics books. Yeah, because I'm not that good at maths, so it's really struggling for me sometimes as well regarding mathematical formulas. So
Okay, I take a note and I try to give you some maybe 3 to 5 book list.
Yep.
Okay.
Well,
Yeah.
I've never used my math case for like in the previous 2 years. So yeah, I forgot a lot of things. So
Math is a very useful tool. Yeah, you can see that a lot of underlying design is based on math.
yeah, it would be really useful if you recommend some books for like entry level, intermediate, or advanced. It would be really useful.
Okay, okay,
Yeah. Thank you so much, sir.
okay. Hi, Gitas. I received your question. I just want to mention to you, I have a back-to-back meeting from can we I will drop you an email and we can talk maybe after 7 p.m. today. Okay.
Sure, definitely.
Okay. Talk to you soon.
Yep.
Okay. Thank you, everyone, for coming.
Thank you, sir.
Okay. Have a good evening. Bye bye.